Hi everyone. In this video, we are going to cover section 3.3, differentiation rules. So we have, in this section, now we will develop all of the tools to take lots and lots of derivatives more efficiently. So I'm going to show you some of them using the limit definition of the derivative, but from 3.3 on out, we are using all of these rules instead of the limit definition. And things get, well, the functions get more complicated, but taking the derivative gets much more efficient, much fewer steps. And so first we have the constant rule. And it says that for any constant, let's see, be a constant, if my function is f of x equals that constant, then the derivative is 0. So basically the rule here, summarizing, right, the derivative of a constant is 0. And that's what that says. We can talk about that in terms of slope. A constant function is a horizontal line. The slope of any horizontal line is 0. We can also look at it in terms of the limit definition of the derivative, right? If I check my f of x plus h, there's no x to plug into in the function, so f of x plus h is just c, and then f of x is rewrite the function, so the numerator of that fraction is c minus c, and so we have the limit as h approaches 0 of 0 over h, which is 0, and the limit of 0 is 0. Right? So basically, you know, there's nothing there. That one's hopefully pretty straightforward. The derivative of any constant is and always will be 0. Next up, we have the power rule. Now, on OpenStax, if you go into section 3.3, they do show, using the limit definition, how this works out. It's a little bit more involved. It takes a little bit more time than I want to get into in this video, but it would be good to take a look at. I'm never going to test you on that or anything, you know, why this is in fact true, but it's a good one to test your algebra skills if you want to take a look at it, how that fraction simplifies. So the power rule says, and we saw in a previous section that when we had an x squared, the derivative was 2x. Well, that kind of holds true for x to any power right here. So if I have my function as x to the nth power, then the derivative of that function is n times x to the n minus 1. So the exponent drops down and becomes the coefficient of x, and then we subtract 1 from the exponent. So as you know, a couple quick examples, if I take the derivative of x to the third power, the 3 comes down, and the exponent gets decreased by 1. So the derivative of x cubed is 3x squared. Or the derivative of x to, say, the 10th power is the 10 comes down, x to the 9th power. 10 minus 1 is 9. Okay, so that is our power rule. On this next slide, we have a lot of words, but really what this just helps us to do is take the derivative of functions that have multiple terms. Okay, so focusing here on the middle, this says the derivative of a sum of functions, but really just think of that as a sum of different terms within a function, is the derivative of the first term plus the derivative of the second term or of the second function. That is true for sums and also for differences. So the derivative of a difference of functions or terms is the derivative of the first minus the derivative of the second. All right, and then last on this slide, we have the constant multiple rule. If I have the derivative of a constant in front of a function, the constant, we can essentially factor that out of the derivative and just multiply it later by what we're left with and just focus on the function, the algebraic part of the term, the x or the y. Well, there won't be y's here, but the x in most cases. All right, so let's scroll down here and take a look at an example of how we use those different rules. Find the derivative of f of x equals 2x cubed minus 6x squared plus 3. And I'm going to expand this out a really long way. I won't expect to see this from you guys in every example, but I am going to for the purposes of the lecture video. Okay, so I want to take the derivative of 2x cubed minus 6x squared plus 3. Okay, so the sum and difference rules from up above say that I can take the derivative of each term individually, 2x cubed, that's a 3, minus the derivative of 6x squared plus the derivative of 3. So I'm breaking up each term and inspecting it and looking at it individually. Now I'm going to use my constant multiple rule and pull that 2 out, and then just focus on the derivative of x cubed. Minus, now I'm going to factor that 6 out in front and just take the derivative of x squared. And then, well, I lost my parentheses, there we go. I can actually take the derivative of 3 right now. That is, the derivative of a constant is 0. So now we only have 2 terms left. All right, let me scroll up to give myself some more space. Now, I can just look at, again, each x term by itself. The derivative of x cubed is 3x squared, but don't forget about the 2 that was in front of it. And the 6 tags along. The derivative of x squared, 2 comes down, decrease the exponent by 1, and it's 2x to the first power. All right, simplifying this, and now finally, I'm going to write my function notation again. The derivative is 2 times 3 is 6x squared, minus 6 times 2 is 12x to the first power, but I'm not going to write that 1. Now, you will get to the point where you can go right from the beginning of the problem all the way to the end of the problem in one step. I don't expect to see that level of detail that I just did, but hopefully that helps you to understand visually and mentally what the process looks like. All right, now let's use our new tools and do an example that we've seen in a previous section, but we can accomplish it a little bit more efficiently. So we are writing an equation of a tangent line to a function at a point. Here's what the steps look like. All right, so our function, f of x, is equal to x squared minus 4x plus 6. That's a parabola. First, I'm going to take the derivative. F prime of x is equal to 2x to the first power minus, now we haven't done an x to the first power yet, so let's do that off to the side. So I want to take the derivative of 4 times x. Well, first, I can take the 4 out and then just focus on the derivative of x to the first power. Well, that's 4 times the x's to the first power, so the 1 comes down, and we subtract 1 from the exponent. 4x to the 0 power is just 4. X to the 0 power is 1, and then 4 times 1 is 4. So that middle term, the derivative is 4. And then the last term, the derivative of 6 is 0. So we have our derivative of our function at any given point. And so now, since I want a tangent line, the next step is to evaluate at the given point. And it says at x equals 1. So we are going to find f prime of 1 by substituting 1 into the derivative. 2 times 1 is 2, minus 4 is negative 2. This guy, remember, that's our m, or our slope. It's the slope at the given point. The last big step is to use the point slope formula. Y minus y1 equals m times x minus x1. And using that, we can write the equation of the line, the equation of the tangent line. But I'm missing something. Do you notice what I'm missing? I have an x-coordinate. I need a y-coordinate. How do I get y-coordinates? And this is part of the thing that sometimes students get confused by. If I substitute into a function, a regular f function, that spits out y-coordinates. If I substitute into a derivative, that spits out slopes. Big difference there. So off to the left here, I want to know what is f of 1. That's going to give me my y-coordinate. F of 1 is 1 squared minus 4 times 1, add 6. So what are we going to get there? 1 minus 4 is negative 3, add 6 is positive 3. That is the y-coordinate. So I have an m, a slope, negative 2, and a coordinate 1, 3. Substituting into my point slope formula, y minus 3 equals negative 2 times x minus 1. Now let's simplify and get it in y equals mx plus b form. Add the 3. Write my answer over here. Y equals negative 2x plus 5. And that is the tangent line to the parabola at the given x coordinate. All right, now we get to the product rule. And the product rule is a little bit more involved than the previous rules. The sum and those were not terrible. This is a bit more to keep track of. And so this is how we differentiate, how we take the derivative of products of functions. So if I have an f times a g, not a plus, not a minus, but two x terms being multiplied by each other. Okay, and so the product rule says, well, you get this big expression for the derivative. It's the derivative of the first function times the regular second function plus the derivative of the second function times the regular first function. All right, and then in terms with the apostrophes, f prime g plus g prime f. Again, on OpenStax, they do go through the proof of where this formula comes from, how we arrive at it. Again, it's using the limit definition, and it involves a nifty little adding and subtracting of the same term that allows us to like break our fraction apart. But again, for length purposes of this video, I'm going to keep that out so we don't drag on too long here. So let's look at an example as I scroll down a little ways. Okay, and I'm going to write down my shorthand for the product rule. If I have the derivative, oops, I don't want to use that color. If I have the derivative of f times g, this is just like my little shorthand, that is equal to f prime g plus g prime f. Got a little messy there. There we go. F prime g plus g prime f. All right, and this guy here is my f function, so for j of x equal to that product, and this guy here is my g part of the function. And then you notice, hopefully, that they are in fact being multiplied together. And it does say to check the result by first finding the product and then differentiating. Again, I'm going to encourage you to go to OpenStax and check out the full solution to this problem. I'm just going to focus on using the product rule. Again, I don't want to make these videos too long. Okay, so what is my derivative? I'm finding j prime of x. The formula says, or the product rule says, take the derivative of f first. F is x squared plus 2. So the derivative of that, the derivative of x squared is 2x. Let me use a parentheses. And then the derivative of 2, it's a constant, is 0. So that's f prime. And now I'm going to write down regular old g. 3x to the third power minus 5x. That's regular old g. Plus, now we have g prime. The derivative of g, 3x cubed, 3 times the 3 comes down, is 9x to the second power. Don't forget to subtract 1 from the exponent. And then the derivative of 5x is 5. Constant times x is just the constant when you take the derivative. Okay, that's g prime, and then times regular f, x squared plus 2. Okay, so what's kind of cool, and you can do this right now if you want to pause the video, if you expand out the original problem and then take the derivative, you will get the exact same thing if you expand out that parentheses, expand out that product, and simplify. You will get the same answer either way, using the product rule or simplifying first. Well, if we have a product rule, of course, we also have a quotient rule. So if I have the difference of a quotient of two functions, that the derivative of that looks like the derivative of the first, or the top, the numerator, times the denominator, minus the derivative of the denominator times the regular old numerator over the denominator squared. Okay, that one looks way more involved, but it's a fraction. Of course, those fraction problems all tend to be a little bit more involved throughout all of our maths. Okay, and that's just the way it is. So again, a little bit more of a shorthand notation: f prime g minus g prime f over g squared. Don't forget to square the denominator. All right, so let's look at that in action. Here is my example. H of x equals 3x plus 1 over 4x minus 3. And then just a reminder, my derivative looks like this. It's f prime g minus g prime f over g squared. Don't forget to take the derivative of the numerator, the top, first. All right, so our h prime, the derivative of h, 3x plus 1, that's my f, 4x minus 3 is my g, and it might even be helpful to, like, off to the side somewhere, write what is f prime, what is g prime, so your, like, brain is in derivative mode first, and then you can, like, switch your brain into let's put the right thing in the right place mode. That's just, suggestion. So if I'm in derivative mode right now, the derivative of 3x is 3. Constant times x. Derivative just leaves me with the constant. Derivative of 1 is 0. And then similarly in the denominator, the derivative of 4x is 4, and the derivative of 3 is 0. Right? So get out of derivative mode. Now put the right thing in the right place. And then we'll have to simplify too. So it's f prime, that's 3, g, 4x minus 3, minus g prime, that's 4, f, 3x plus 1, divided by the denominator squared. Okay, so if it helps to do that separately, and you can do the same thing with the product rule if you found what I just did to be helpful. Okay, one thing we do need to do is clean this one up a little bit. So I'm going to rewrite my h prime, distribute the 3 into the first parentheses, 12x minus 9, distribute a negative 4, don't lose the negative, into the second parentheses, negative 12x minus 4, right? That negative 4 distributes to both terms. And then that's divided by 4x minus 3 squared. All right, we can clean this up a little bit better. 12x minus 12x is gone. Negative 9 minus 4 is, let's see, that should be negative 13 over the quantity 4x minus 3 squared. And there's your derivative. Now, if you go back to earlier in the video, when I first had up the power rule, that said that it was only true for positive integers. And the way that we prove that at the beginning of the section, even though I didn't do it in the video, it does only hold for positive integers. But what's kind of cool is as we've gotten these additional rules, we can use them to take that power rule that's only true for positive integers and then extend it so that we say, no, it's actually also true for negative integers as well. And then actually later in the course, or later in this chapter, we'll say, oh no, this is true for, like, fractions and stuff too. We'll get to that, so hang tight there. But what I want to do is show you if I have a negative exponent, okay, if k is a negative integer, I can use the quotient rule. So if I want to take the derivative of x raised to the negative nth power, or another way to write that is the derivative of 1 over x to the positive nth power, right? So I'm dealing with a negative exponent, so I'm writing it in the denominator, okay? What I can do is use the quotient rule because I've got a fraction. I can use the quotient rule to take this derivative, and it looks kind of cool as we do it. So first I'm going to do the derivative of the numerator, which is 0, times x to the n. All right, and then I'm going to subtract the derivative of the denominator, which is n times x to the n minus 1. Exponent comes down, subtract 1 from the exponent, and I'm going to keep my numerator the same. So this is, let me get my pointer. This is f prime g minus g prime f, and then don't forget that is over the denominator squared, x to the nth squared. All right, well, that looks very messy, so let's clean it up. First term drops out because it's 0 times x to the n. So this is going to simplify to negative n x to the n minus 1 times 1, so I'm not going to write that, divided by x to the n to the second is x to the 2n. All right, we're getting a little bit cleaner. Now the last step is I want to simplify and write just x in one place. There we go. All right, and since I'm dividing, I have the same base, so I'm going to subtract the exponents, n minus 1 minus 2n. Subtract the exponents, and that simplifies to negative n minus 1. And so plugging that into my answer, negative n x to the negative n minus 1. And that looks almost like the extended power rule that I have written up above, kx to the k minus 1. And the difference here is that in my parentheses, I had x to the negative n. Here it's x to the positive k. They're opposite of each other, and so that's why we ended up with opposite signs there. But long story short, if you have a negative exponent, you use the power rule in the same way. Okay, and how does that make my life easier? If I want to take the derivative of 1 over x to the 7th, g of x is 1 over x to the 7th. I don't want to use the quotient rule because that's much more complicated. I can bring that 7 up with a negative exponent and then use the power rule. Negative 7x to the negative 7 minus 1. And I'm going to write this down because people always make mistakes with this one. Negative 7 minus 1, it's negative getting more negative. So negative 7x to the negative 8. So I can leave my answer that way, or g prime of x is negative 7 divided by x to the 8th. Okay, a couple different ways to leave that answer. All right, again, long story short, if I have an x in the denominator by itself, bring it up to the numerator with a negative exponent, and it's much more efficient just to use your power rule. All right, let's go through two more application problems where we use all these tools. So in the first one, we want to find out where a function has a horizontal tangent line. Horizontal tangent line. And just as a side note, that's a little star there, that's where the derivative is equal to 0. Horizontal tangent lines, that's where my derivative is 0, where the slope is 0. So my steps are as follows. I want the derivative first, x cubed, 3x squared, 7x squared, 14x, 8x, just 8, derivative of 1 is 0. Boom, step 1. Step 2, set it equal to 0. That's because I'm specifically told I want that horizontal tangent line. We'll set it equal to 0. I'm going to see if I can factor that trinomial. 3x goes here, x goes there. Factors of 8 are 4 and 2. And as I was recording this video, I paused it for a minute so I could think about what the factors are. So I'm not just off the cuff, off the top of my head, writing down these factors perfectly. If you use a little bit of trial and error here, that's absolutely fine. All right. And the signs are both negative. And the reason I know that that is correct is because when I check, that's negative 2x. That's negative 12x, which is my negative 14. All right. But getting back into it, we're going to set it equal to 0. And then I want each factor equal to 0. X minus 4 is 0. 3x minus 2 is 0. So this function has two horizontal tangent lines, one at positive 4 and one at positive 2/3. One last example involving velocity. So if my s function, s of t is my position function, is t over t squared plus 1. That is the position of an object on a coordinate axis at any given time t. What is the initial velocity? Initial means starting. So that is at the beginning of time when t equals 0, right? But the velocity tells me that I need the derivative. So those two words together tell me I need to find s prime of 0. Initial beginning, that tells me the 0. Velocity is the derivative of my position function. Look at the function and you say, oh no, it's a fraction, so we use the quotient rule. Okay, so our derivative, s prime of t, start by differentiating the numerator. Derivative of t is 1 times t squared plus 1. Then we differentiate the denominator, 2t times the regular numerator, t, divided by t squared plus 1. Now for this one, I'm not going to worry about simplifying it because they just want me to evaluate s prime of 0. So I'm going to plug 0 in right off the bat. 0 squared plus 1 minus 2 times 0, that's super 0, divided by 0 squared plus 1. That drops out. That's gone. That's gone. I'm just left with a 1 in the numerator, 1 in the denominator. So the initial velocity, the velocity at the beginning of time for this object, is 1. And we're not going to write any units here because we're not given any units in the problem. 1 unit per unit of time. But no, that would be silly to write down. All right, so lots of rules in this section. Think of them as ways that we can take derivatives of lots of functions. Go back, review them, work on some homework questions. Please let me know if you have any of your own questions. And thank you very much for listening. Have a wonderful day.